So good afternoon, everyone. So welcome to lecture 36 of the course on data structure and algorithm. So in the last class, we have discussed about a concept of threaded binary tree, and today in today's lecture, we shall be talking about discussing about few small topics. First of all, we will prove an important I mean formula, important statement regarding a binary tree, which is very popular and frequently coming in a semester exam. And the next topic is we will discuss about a 2-3 tree. 2-3 tree. It's a special type of general tree. Okay, the general tree is a generalization of a binary tree, where in binary tree any node may have at most two children, but in general tree, more than two children are allowed. Okay, so that is a general tree, and one special type of tree is 2-3 tree. We will discuss about today, and with the help of an illustrative example. That example which was appeared in the last year second class test question paper. Acha. Next, I will show you the code implementation and its illustration of the binary search tree. Okay, so some of you have exam tomorrow, and they will require the understanding of the code implementation of BST. That's why. Anyway, so I've shared my screen. Hope all of you can see my screen. Is it visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so is the font visible to all of you? Can you read the lines? Hello?
Yes, sir, we can.
You can, right? So it's fine. So the question was like this. So this was the question. Okay, so this was the question. So prove that for any non-empty binary tree, the tree name is capital T. So if n0 is the number of leaf nodes or leaves, and n2 be the number of nodes with degree 2. So this thing, my suffix 2 signifies that it will have a degree 2. So similarly, n1 is the number of nodes with degree 1, n3 is the number of nodes with degree 3. So this is a popular thing which we need to prove, n0 equal to n2 plus 1. And another thing is n0 equal to n3 plus 2. So I will show you the proof of this, n0 equal to n3 plus 2, because it is not available in the book. Okay, so n0 equal to n3 plus 2. Okay, so this is the question. So prove that for any non-empty binary tree, n0 equal to n3 plus 2, where n0 is the number of nodes having degree equal to 0. No children, okay, sorry, n0 is the number of leaves, okay, and n3 is the number of nodes with degree equal to, okay. So let's see the proof here. Degree 2, n2, okay, n3, okay, n3. Where is n3? Right. Now, okay. So before this, actually, this proof requires some prerequisite knowledge about some theorems on graph. So tree is a special graph, one kind of a graph, which is acyclic graph. So I just in after few lectures we shall start the discussion on graph. But today, just I will tell you those concepts of graph which will be required to understand this proof. That's all. Okay. So okay. So consider two different data structures. This is one data structure containing 4 nodes, and this is another data structure containing same 4 number of nodes. Okay, but their structure is different. Here they are connected like this. So this is a cyclic graph. It's a cycle. You can call it some cycle or cyclic graph. It's a graph. Okay, so if I connect this, so this is also a graph. So both of them can be treated, are called graphs. But here, okay, this is a cyclic graph. This is an acyclic graph. Cyclic graph, and this is acyclic graph. Okay, so one point through which we can distinguish which one is cyclic, which one is acyclic is that. So if I start a journey from a node, then I can return back to that node in a cycle. But if I start journey from a node, I may not return back to that initial node from where I have started my journey. That is the acyclic graph. So in this case, this is a special acyclic graph. Here we can call it as a tree or binary tree. Our example is, in this case, a binary tree. What is a binary tree? Binary tree is a tree. It's a data structure where a node may have at most 2 children. So this node does have 2 children. This node. This is the left child. This is the right child. Okay. This node is having only a single child. That is the left child. This node is a leaf node. Why? Because it does not have any children, any child. No left child, no right child. So either a node may have 0 number of child, or a node may have 1 child, or a node may have 2 children. But never a node can have more than 2 children. So that is a binary tree. Okay. So this is an acyclic graph. And in acyclic graph, so these are leaf nodes. Okay. So as binary tree or any tree can be termed as a graph, and in a graph there are a few terminologies like a degree of. In graph we call this kind of nodes as vertices, and in tree we want to call these nodes as nodes. Okay, so these are the difference in terms of terminologies which are used in graph and tree. So as this is a tree, we will call these as nodes, and as this is a graph, so we will call them as vertices. Okay, so in a graph there is a popular theorem on a graph, that is, for any graph, okay, for any graph, for an acyclic graph, so number of, okay, we will come to that theorem later. First try to understand the degree of a vertex. Degree of a vertex. What is degree of a vertex? Degree of a vertex means simply the number of edges incident on that vertex. For example, this vertex, this is a graph, so I can call it a vertex. So this vertex, okay, this is vertex number 1, this is vertex number 2, vertex number 3, and this is vertex number 4. These are not values, these are levels. Vertex number 1, vertex number 2, vertex number 3, vertex number 4. So vertex 1 edge is incident on vertex 1. So its degree will be equal to 1, and we denote like this: d of 1 is equal to 1. Okay. So similarly, this vertex 1 in edge, this is an edge. What is an edge? These are called edges. How many edges in this acyclic graph? 3. 1, 2, and 3. So 3 edges are there. How many vertices? 4 vertices. So 4 vertices, 3 edges. So this edge is falling on or is connected to this vertex, and we call it like this edge is incident on this vertex. How many edges are incident on vertex? 1. That is 1. That's why its degree equal to 1. Similarly, for vertex 4, how many edges are incident on vertex 4? 1. So degree of vertex 4 is also equal to 1. Okay, but for vertex 2, so this edge is incident on vertex 2, this edge is also incident on vertex 2, or in other words, in simpler words, two edges are connected with vertex 2, so its degree will be equal to 2. Degree of vertex 2 is 2, and so as degree of 3, right? Am I correct? Degree of vertex 3 will be also equal to 2. Is it fine?
Yes, sir.
Yes, sir.
Right? So now we got to know what is the degree of a vertex in simple cases. This much knowledge, if you have, that's fine. So what is the degree of a vertex? Number of edges connected with the vertex. That is in simpler words, or more technically, number of edges incident on a vertex is called the degree of that vertex. That's it. Okay, and you can find in the cyclic graph, okay, this cycle. So in short, this is denoted by C4. This is a short. C4 means it's a cycle of 4 vertices, and the structure will be like this. Similarly, basically it's a quadrilateral, right? It's a quadrilateral, 4-sided polygon. So what is C3? C3 is a rectangle, a triangle. This is a vertex. This is a vertex. This is a vertex. So we can denote mathematically this representation as a capital C3, and it's a cycle of 3 vertices. Similarly, you can have a pentagon. So it is C5. It's a cycle of 5 vertices. C5. So that means, and so on. You can represent any k, ck. So it's a cycle or cyclic graph of with k number of vertices. So k-sided polygon it is, right? So in a polygon or in a cycle, all the vertices are of same degree. For example, in C4, all the vertices are having degree equal to 2. Okay, 1, 2, 3, 4. Here also, the degree of all the vertices are actually 2. Okay, am I correct?
Yes, sir.
Yes, sir.
Oh, so this is fine. So now, one important theorem or observation, that is for an acyclic graph, the number of vertices will be always equal to the number of edges plus 1. Or mathematically, what we can write. So if I denote the number of vertices, normally number of vertices in a graph is denoted by small n, and number of edges in a graph is denoted by small e. So this is number of edges, number of vertices, and this is number of edges. Number of edges. Okay. So then mathematically what we can write, the theorem is n equal to e plus 1. Okay. Number of vertices equal to number of edges plus 1. That is the theorem with which this proof is started. So as T is an acyclic graph, we have a number of vertices n equal to the number of edges plus 1, n equal to e plus 1. Where n is the total number of vertices, e is the total number of edges. So this is equation number 1. And then from the given problem statement, that n3 is the number of vertices with degree equal to 3. And what do you mean by a degree 3? The vertex to which 3 edges are incidenting. So 3 edges are connected to a vertex. Those vertices will be having degree 3. So number of such vertices with degree equal to 3, let's assume that be n3. Okay, and n0 is the number of leaf nodes. And what is the degree of a leaf node? Who will tell me? What is the
Zero, sir.
huh?
1, sir.
Yes,
Zero.
1. So this
Oh,
is a
one.
leaf
One.
node. This is a leaf node. Only one edge is incident on that leaf. So N0. N0 is the number of leaves. As per the problem, N0 is the number of leaf nodes. Okay. And N2 is the number of vertices with degree equal to 2. Okay. So then what we are getting? So what is N? N is the number of vertices with degree equal to 1. That is number of leaf nodes. Yes or no?
Yes, sir.
So I mean to say the n is the total number of vertices. The total number of vertices means in a tree, which is nothing but a graph, in a graph or in a tree, there are different type of vertices. There are different type of vertices in a binary tree. We are given a binary tree. So in a binary tree, the maximum degree possible. What is the maximum degree possible in a binary tree?
So two.
No, the maximum degree can be 3.
Yes, sir. Three only.
Suppose this node number 3 is having both the children, left child and right child, and also it may have its parent. So 3 edges are actually incidenting on that vertex, right? So this is the thing, but we cannot have another edge like this. Can we have another edge, another branch from this vertex 3? Is it possible?
No, sir. Binary tree, sir. The binary tree, sir.
It's a binary tree. Yes, that is the thing. So one observation we have made from here, that is the clue that the maximum possible degree. This is very interesting. Maximum possible degree of a binary tree is equal to 3. So that means in the tree, okay, what is the minimum possible degree? Minimum possible degree of a
0.
of not of you can have in a binary tree.
So 0.
1.
Okay, so someone said 0. So 0 means number of edges falling on that vertex is 0. That means no edge is actually connected with this node or vertex. So can we have a tree at all where a node is not connected with any edge or branch?
No, sir.
Is it possible? Is it possible? Any tree, whatever you are actually constructing, okay, whatever tree you are constructing, see all the nodes are some way connected or grouped in a single entity, in a single structure.
So we can't consider the first initial state.
হ্যাঁ
স্যার ফার্স্ট ইনিশিয়াল স্টেটটা তো কনসিডার করা যাবে না, কারণ তাহলে ট্রি তৈরি হচ্ছে না।
No, that is not the case. This is a tree, but these are null. Okay, so these are null. So that is not the problem. Okay, so the thing is, if okay, so so this node, suppose this is a tree, okay, and suppose this is I mean another tree which is and this is not a tree, this is a node. This is a node. We can't call it as a tree. This is a node. Okay, because this is a single node. We can't call it as a tree. So tree to tree, it will be termed as a tree when a structure will be like this. At least we can't call it as a tree, as a distinguished tree. It is a simple single node itself. Suppose an isolated node is placed over here, and this is a tree. Okay, so then is it possible this overall data structure a tree? Can we call this overall data structure as a tree? The answer is no. because this node is not connected with the other portion. Okay. Also, if we have two trees like this is a tree, this is another tree, but can we call this overall data structure as a tree? No. This overall data structure does have a very special name, very beautiful name, that is forest. The forest is a collection of trees, disjoint trees. So this is a tree, this is another tree, but they are disjoint trees. So a set of disjoint trees is known as a forest. অনেকগুলো গাছ হয়ে যেমন একটা জঙ্গল হয়, similar concept. Okay. So this is fine. These are there. So this is not possible. So if there is a node which is not connected with any edge, that cannot represent a tree. But if it is not connected with any edge, so its degree will be equal to 0. Degree of this equal to 0. And this is not possible in a tree. So we can't have a degree in a binary tree as a 0. So minimum possible degree in a binary tree is 1 and maximum is 3. So that means what? There are several type of vertices, of which, so there are vertices possible with degree 1, 2 and 3. Understood? So the vertices which are having degree equal to 1, the number of vertices with degree equal to 1 is denoted by n0. The number of vertices with degree equal to 2 are denoted by n2, and number of vertices with degree equal to 3 are denoted by n3. That is what given in the picture. So, and if we sum them up, number of vertices with degree equal to 1, number of vertices with degree equal to 2, number of vertices with degree equal to 3, if we add them, we will get total number of vertices in the tree. So that is what written over here. N equal to n0 plus n2 plus n3. N0 is the number of vertices with degree equal to 1, that is the number of leaf nodes. N2 is the number of vertices with degree equal to 2, number of vertices with degree equal to 3. Okay. So total number of vertices n equal to e plus 1. That is from equation number 1. So this is fine, right? Now n0 plus n2 minus 1, bring 1 in the left hand side and n3 in the right hand side, we get e minus n3. So somewhat this kind of equation we are getting. N0 plus n2 minus 1 equal to e minus n3 after rearranging the terms. Now by theorem, we have another theorem. The degree sum equal to the twice of edges. So we have another theorem on a graph. It's a very popular graph. While discussing about graph, I will also show you the proof of this theorem. Today we don't want to prove them, just we want to use them. The theorem is, in a graph, the degree sum is equal to twice the number of edges. So in expression, it is denoted as, so degree sum. What is a degree? A degree of any vertex D is denoted as di. Okay, the degree of an ith vertex, and we want to sum up all such vertex. Right, sum of all such degree vertex, the degree of a vertex I, the sum of all such vertex I equal to 1 to n, right? That means d1 plus d2 plus d3 plus dot 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 up to dn. So degrees of all the n number of vertices we are summing. Okay, so this summation will be twice of e, where e is the number of edges, and n is the number of vertices. That's it. So it's a very popular theorem. Okay, and so degree sum I equal to 1 to n, degree of any vertex vi, and we are summing them for all the n vertices. That is equal to twice of e. So n0, so degree sum means, So yeah. So now look on this thing. So what you will get, that is, we will have some vertices with degree equal to 1, and we will have some vertices with degree equal to 3, and we will have some vertices with degree equal to 2. Okay, so I mean, don't consider this line, so just directly you can write this line. So n0 plus 2n2 plus 3n3. So let me write over here this expression here. Okay, so the left hand side is the summation of all the degrees of all the vertices. So there are vertices there, so we can write like this. So there are vertices of degree equal to 1, degree of all those vertices of with degree equal to 1. That means all those n0 summation over n0. Here it is right. So this is true summation of all the vertices which have degree equal to 1. So we are summing up the degrees of all n0 number of vertices. Right? Of the background noise. So we are summing up the degrees of this n0 number of vertices. What are the n0 vertices? N0 number of vertices are having degree equal to 1. Similarly, we are summing up degree I, suffix I. Okay. Right. For all n2 number of vertices which have degree equal to 1. Similarly, plus summation, so di, right, for all n3, right, and that is equal to 2e, right. So one vertex has a degree 1. Two vertex will have total degree 1 plus 1 2. So here n0 number of vertices will have degree sum equal to what? n0. প্রত্যেকটা ভার্টেক্সের ডিগ্রি যদি 1 হয়, এবার যোগ করো n0 খানা ভার্টেক্সের ডিগ্রি যোগ করো, কি পাবে? n0. So n0. Here each of the vertex in this group, n2 number of vertices group, so each of the vertex does have degree equal to 2. So if you sum their degrees, so they will contribute to how much? n2? 2 n2. Yes. Similarly, if you sum the vertices, degrees of the vertices in this set of n3 number of vertices having degree equal to 3, so they will contribute to 3 and 3, and that is equal to twice of e. That is what written in the here. n0 plus 2 n2 plus 3 n3 is equal to twice of e, and that e is replaced by the expression coming from equation number 3. What is e here? E means n0 plus n2 plus n3 minus 1. That is written n0 plus n2 plus n3 minus 1. So multiply 2n2 plus 2n0 plus 2n2 plus 2n3 minus 2. So 2n2 get cancelled. Ultimately, what we are getting after rearranging, n0 equal to n3 plus 2. Yes, the proof is very straightforward, very small proof. But yes, to do the proof, we require this basic understanding, prerequisite knowledge about little bit of graph. Two theorems are utilized over here, used. Okay, so next we come to it's 111, 233. Okay. So I think I will be running out of time. So let's see. So let me show you the program code implementation of BSD. Then if I have some time, I will show you 233 or in the next class. So have you seen the code?
Yes, sir.
Okay. So this is the program of the binary search tree. Uh, with the binary search tree. So, okay, let me explain. And what I want to, it's okay. It is done. I'm not praising myself, but it is done quite comfortable, beautifully, because we can actually easily visualize and justify our program very well. Yes, this program is working very fine. Also, whatever tree, data structure, logic, block diagram we used to draw in our copy to understand binary search tree, so that can be visualized through this program code. That's why I want to show you how it is done. Okay, so fine. So in order, insert BST. So insert. Okay. There's a concept. Okay, call by reference. Okay, fine. So this is the main function. The main function option value start with root is the pointer which is supposed to point towards the root node always in a binary tree, binary search tree. Initially it is null. Then infinite loop comes. Here's the menu option. Insert, delete, in order, pre-order. Okay, right. So switch case. So case 1 insertion, case 2 delete, case 3 in order, case 4 pre-order, case 5 post-order. So for firstly we want to concentrate on insert and delete and in order. Achha, insert BST. So while calling the function insert BST, we are passing the arguments, two arguments. One is ampersand root, another is value. Value variable stores the value given by the user, which is going to be inserted in a binary search tree. Okay, and other parameter is ampersand root, means address of the pointer named as root we are passing as an argument. So it's a call by reference phenomena feature we are using. Okay, and that is okay. Here is the function definition: insert BST. The picture. Okay. Okay. Please carefully observe. So root is a pointer where some address will be stored. Initially it is 0 because it is pointing towards null. Okay, and then this root pointer itself does have an address. Let's say that is 2408. Okay, that is the address of root. Ampersand of root is this, and root is a pointer, so it itself stores another address. So it contains an address. Okay, that address is initially 0 because it is pointing towards null. So that address of root is coming as a parameter due to call by reference feature. Achha. So as it's an address of a pointer, so who can receive? A pointer to pointer can only receive an address of a pointer. That's why a pointer to pointer is used here to collect the incoming address of a pointer. Star P. The star P means P is actually receiving the incoming value. What is the incoming value? Ampersand root, address of a pointer. So address of a pointer is collected by the pointer P. Here P is not a structure pointer. It's a structure pointer to structure pointer. But if I apply star P, then it will give us root. Okay, so let me draw a picture here. P. Okay, so this is the picture. Okay, so P is actually pointing towards root. Okay, So pointer to pointer. And so if I apply star p, so if I apply star p means value at the address specified by p. So what is the address specified by p? 2408. So go to the address 2408 here. What is the value? 0. So star p equal to 0. And what is the root value? 0. So star p equal to root. Star p equal to root. I hope now all of you have understood this point. Is it okay?
Yes, sir.
Yes, sir.
Yes. Is this picture clear to everyone? Call by reference?
Yes, sir.
Okay. Fine. So now int value, the other parameter. So here if star p equivalent to, okay, this is for the stopping criteria of the recursive function call. So here we have done recursive function call. Okay. So initially star p equivalent to null. Yes, it is true. Initially star p equivalent to null. What is star p? Root. Root is equivalent to null. So printf position found for, it's a message, position found for possible insertion. What we are doing memory allocation, blank memory allocation. In the picture, the right hand side of this line means what has happened? Okay. Okay, this kind of a blank memory allocation is done, and its address will be something, let's say 1100, address of this overall node. Okay, fine. So that address will be assigned to star p. Star p means, what is star p? See what I am doing through this code. Very handy this is. Why? Because star p is equal to that address, memory address, memory allocation. Address after memory allocation. So what is the address after memory allocation? 1100. That means 1100. So star p equal to 1100 means, what is star p? Value at the address specified by p. The address specified by p is 2408. So inside for 2408, what is the content? This is the content. So this is star p. So this will be assigned the value 1100. See what we are doing. We are never using the root variable, but through this p pointer, pointer to pointer, we can directly update the root value. Okay, just from using star p. So that is the fine. So I can write over here, star p means this one. In this case, this one. Okay. So this is done. Next, so by this what happened? Root is actually pointing towards this node. This is the first node in the binary search tree. Next, star p pointing level. Star p means 110. This is, so if I do not do this, so far what we have learned, conventional process, that is, here you used to write a pointer temp equal to struct based node. Am I correct? Temp. Instead of star p, you used to write temp. So temp means you are taking use of another variable, temp, and temp is supposed to hold this address after memory allocation. But here we are not requiring a temp. Rather, using star p, we are directly modifying the content. Modify the content of root. Okay. Okay. Fine. So star p pointing level is equal to value. So let's say first we want to insert a value, let's say 11. Star p means this one, star p pointing level is equal to 11. Star p pointing left null, star p pointing right null. Right. So this is star p pointing left, star p pointing right. Those are pointing towards null. Next, return 0. Return 0 means it will from 75 number line, it will come back to 70 line number 32. And next, break. Break means it is coming out of switch. So out of switch means this bracket. So after this bracket, what is there? The close of switch. Then it is end of while. Yeah. So again it is coming to while loop, coming to line number 25, because while condition is true, it's an infinite loop. Line number 25 showing the menu option message. Again you want to insert, let's say option is 1. So again you want to insert. So insert BST function is called ampersand root value. So now what is the value of ampersand root? In terms of this picture, from this picture, what is the ampersand root? What is the value of ampersand root?
So 1100.
No, 2408.
2408.
1100 is the value of root.
Oh, value of the root. Okay.
Okay, so ampersand root is 2408 and value is some user given value. Let's say 9. So with this two information, function is called. So function is coming here, right? So here p equal to ampersand root, p equal to 2408, and star p equal to 1100, and value equal to 9. Is star p equivalent to null? Star p is the value of root. Is root equal to null? No. So it will go to else part. So user given value, that is 9. Is 9 greater than or equal to star p pointing level? Star p means this address 1100, and of which label value is 11. So is 9 greater than or equal to 11? Is this satisfied? No. So this if is false. So it comes under else part. So we recursively call insert BST, this function itself. So what is the prototype? To call insert BST, we need to pass an address of a pointer, because it's already mentioned a pointer to pointer. So I can't pass any random variable, any random value. I must pass an address of a pointer, and next an appropriate integer value. So of course this is the value variable through which I want to pass the value 9. Okay, and what is the address I should pass now? So as 9 is not greater than equal to 11, means 9 of course is less than 11. So what should I do if 9 is less than 11? I want to go towards left subtree. I want to go towards left subtree, and I want to reach to the next node in the left subtree, right? So I must pass the address of the next node in that left subtree. So how to get the next node? How to get the left address of the left child of this node? The next node of this node is the left child. So how to get the address of the left child? I know
Star P pointing left.
star p. I know the address of this node is star p. So star p, which is this current node, and its left child means star p pointing left. Okay, so this is pointing left. Okay, so this is giving you the this is giving you, suppose let me draw a picture of a child node, then you will understand. Suppose this is the scenario. Okay, so star P pointing left. So suppose this is 1200. Suppose. So it is storing here 1200. Okay. So star P pointing left means 1200. This means 1200. So we must pass address of this 1200. Means address of star P pointing left pointer. What is this? It's a pointer. Yes or no? Is this a pointer or not? My goodness. This is the structure of a node, right? 3 parts are there. Left part, right part, middle part. Left part is star BST node star left. Middle part is an integer variable. Right part is a pointer named as right. So this is but a pointer. This is also nothing but a pointer. These are actually pointers, structure pointers. This pointer is supposed to hold an address of the left child. This is supposed to hold the address of the right child. So star P pointing left means the value of this pointer, and we want to pass the address of this left pointer. Okay, so what will be the syntax? পুরোটা একটা ব্র্যাকেটে দাও। পুরোটা একটা ব্র্যাকেটে দাও স্টার পি star P pointing left. This is the left pointer and we want to pass address of this pointer. So before it we want to write this. This is the syntax. Ampersand of bracket A star P pointing left. Now see. So this is star P pointing left, which is written inside another bracket, and before it address ampersand is given. So ampersand of the left child pointer is passed. We must pass this because star P can't collect star P pointing left. It has to collect some address of another pointer. That's right. So this is the breakthrough. Once we understand this, insert BST function understanding will be complete. My 50% is complete. Okay, so we are calling this function like this. So what happened here? Let me clear the picture a little bit. So there is no node, right, as per the scenario. Okay, so this is the picture. It is null. So what I am passing? Address of a pointer which is star P pointing left. This star P pointing left is nothing but null or 0. So we are passing the address of a pointer which is actually holding an address 0. Okay, this kind of thing we are passing. So from this function call, it is coming to this line number 66. Okay, where star pointer P is collecting that information, ampersand of this. Okay, so not this P, another duplicate P will be created because due to the recursive function call. This is the meaning of a recursive function. Okay, so another duplicate P which is receiving the incoming address of this pointer. And what is this address of this pointer? Let's say random, let's say 1200. Address of this pointer, address of this left child pointer. Which address? Address of this pointer, that is 1200. So it is now stored in P. Okay, so next is star P equal to null. What is star P? What is star P? Star P means the value at the address specified by P. What is the address specified be? 1200. Means go to the place 1200. This is the address 1200. So this is a pointer. Okay. Yeah. Okay. So there are three parts: left child pointer, right child pointer, and integer variable. And each of these three parts will have their own address. So this right child pointer is having some address, let's say 1300. Address of this left child pointer is, let's say, 1200. For example, address of this integer variable, say 9, say 110. Okay, 110, 110, and this overall entity will have an address, let's say 1100, for example. Okay, so this is the concept. Now star p means go to the address 1200. Here, what is the value inside it? 0. Why? It is pointing towards null. So now, is star p equivalent to null? Yes. Logically, what does that mean? Is the left child pointer is available? Is it open? Is it pointing towards a null? Yes. That means a position is available for insertion. So message is printed, position found for possible insertion. And next, you are doing a memory allocation, another blank memory for a node. Okay. Okay. It will have its own address. Let's say 900 is the address of the overall node. Okay. That address 900 will be assigned to star p. What is star p? Star p means the value inside 1200. Value inside 1200 means this one. So here 900 will be stored. Here 900 will be stored. So that means what? This is no longer pointing towards a null. This is now actually pointing towards this overall node. Okay, the left child. So this node now has a left child in this manner. And here the value 9 is stored. With a star point p pointing level equal to value. So due to which 9 is assigned here. Next, star p pointing left null, star p pointing right null. So this is null, left null, this is null. So this is the fundamental concept of an execution of a recursive function called insert BST, and this is the complete picture for understanding. Okay, so it is done. Return 0. Return 0 means it will return to that position from where this recursive function was called. Means this position from where this recursive function was called. So here it will come back. In the picture, it is coming back to here. Here the ampersand of that star p pointing left was passed. Here it will come back in this way. So after execute completion of this line, next else part is completed. Return 0. Return 0 means it is coming back to this line. Then break, coming out of switch. Then end of while, again coming to condition. While condition is true, satisfied. Coming to line number 25, showing you the message insert, delete, in order, pre-order, post order. Again, you are giving an option, insertion or deletion, whatever, or in order, whatever, based on that. So let's say insert BST, another value you want to insert. Okay, So let me ask you, with this I want to conclude today's lecture, but before that, okay, one thing I forgot, whenever this recursive function was called, the 9 value, when this thing happened, after completion of this thing, so I told you, return 0 means it will come back to this position from where the function was called, right? So whenever it was returning back to this position, this temporary p will be removed, will be erased from the memory. This is like a concept. So during recursive call, function call, there may be lot of variables, temporary variables, which are created, but their memory allocation are done in the runtime scenario. So this is like that kind of a variable p, which is of which memory allocation is done in a runtime scenario. And if the recursive function is completed, then all those temporary memory allocations will be automatically deallocated. Okay. Also, this p will be deallocated because these are formal arguments. Whatever formal arguments are used, okay, whenever you want to call a function, this is a function call, this is actual arguments, these are formal arguments. So when you call a function coming to this position, so due to the formal arguments declaration, p value, p pointer, value variable, memory allocation of this p and value will be done in a runtime scenario. When this function execution is completed, its process, then all those memory allocation of formal arguments, okay, or these local variables, whatever here present, all will be deallocated. So I mean to say, after insertion completion of this 9, what will happen? The picture will be like this. The picture will be like this. Like this. There is no p. This is the picture. Next time when again you call insert bst ampersand root, and then it is coming here, then again it is saying that, okay, memory allocate memory for p and value, let p store the value of ampersand root, let value variable store the incoming value, let's say some 9 or 13 like that. So this is what happened. Okay, sir? So if again insert bst function is called, let's say now value is equal to 13. Let's say value equal to 13. So can you explain the process, execution process? Now the value is equal to 13. So of course I know that this will be connected to something. This will be the picture. This is the picture, right? After insertion of 13, this will be the picture. So can we explain the code, how this process will be done? How this process will be done? So it's a mechanism. You must understand the mechanism. Anyone can explain?
Sir, Volvo.
Sure. One by one.
Okay.
Sir,
Sir, after coming to this, the formal arguments, the star p and the value are being assigned. So at first, yes, sir, the star p is assigned to root, and then we are checking about the availability of the right child of the root by checking that the ampersand of a star p pointing right double equals to null. If it is equals to null, then the right child is being allotted.
Okay.
Yes, sir.
Okay. Up to this is done. Next, we are coming here, line number 68. Line number 68. Bolo.
Yes, sir. After that, we are coming to line number 68, and here we are checking if star p double equals to null. As it is not equals to null, then it will go on to the else part, and the first part of the else part will be activated. I mean, that line number 79, yes, 79 and 80 will be executed.
Why? Why?
So yes, sir, be explaining. So because at first it is coming to the else part because as the tree is not empty. Okay. Then after that in the else part, line as it is mentioned that if 13 is greater than value, the 13 is greater than the
What is
stored
star P
value, that is
pointing
the root
level?
value.
What is
Yes,
star P
sir.
pointing level?
So
In the
star p pointing level is the value of the root, that is 11.
star P means 1100.
Yes, sir.
Star P
1100.
pointing level means this portion.
Yes, sir. This portion, that is 11.
That is 11.
So
Okay.
as the incoming value 13 is greater than 11, so it will be added to the right side of the so it will be added to the
It is
right
fine.
child of node
We are
11.
technically speaking, we will be adding to the right side. There is nothing, no code is written here calling that right side, left side. So next program execution. That means this condition is satisfied.
Yes, sir.
Then this recursive function insert BST will be called.
Yes, sir.
It means it will now move towards right branch,
Yes, sir.
right subtree. So what will happen through this recursive function call? What are the arguments?
Yes, sir. Hmm. Sir, in the recursive function call, first of all, there is the right child of the root node, that is the star p pointing right, that is the ampersand, that is the address of this one, that is 1300 is being passed.
Star P,
1300.
achha, what is star? First, tell me is star P pointing right.
So star p pointing right is the value that is being stored in the right child of root.
In this picture, what
Sorry,
is
right part of root. Right part of root, not right child.
in this
Sorry, right
picture?
part of
What is
root.
the value of star P pointing right?
0.
Yes, this now. So star P
Yes,
pointing
sir.
down means what the value of the right child pointer. This portion. What is
Yes, sir.
stored here? That is 0.
Yes,
So
sir.
this is like something 0 or null and ampersand of such thing.
Yes, sir. That is 1300.
And this is 13. Very good. 1300. I think now all of you have understood. Key 130 is the address of the right child pointer that we are passing to this function call.
Yes, sir.
So due to the function call, it is going to which line?
Yes, sir. So after this, due to the function call, it is going to the line number 66 line.
Yes. Now explain this here.
Yes, sir. So in this line, we are again coming to the initial state where is another temporary pointer, that is p, that is the same name pointer p is been assigned, and this time the value is being stored in another node, in another new node.
Wait a second. P. Tell me what is the value of P?
So now the value of p is 1300
Hmm.
star p.
Value of P is 1300, right?
Sorry, hey, sir. Value of p is 1300. Yes, sir.
And star P.
Star p is 0.
Hmm. Fine.
Yes, sir.
Next, value equal to 9. Hmm.
Yes, sir. Value equal.
18.
Yes.
Next.
Yes, sir. Sir, after that we are now coming in this part, that is if star p double equals to null, as it is true because star p equals to double equals to null.
Hmm.
So now we are creating a new node,
Hmm.
that is a right child of root.
Let's say the address of that new node is 3004. Okay.
Yes, sir.
And here we are inserting a value 13.
Yes, sir.
Okay, that is fine. So next line. So explain this line 71. So the
Yes,
address
sir. Yes.
3004. Then
Sir, yes, sir. So in the line 71, a new memory allocation is being done. Dynamic memory allocation is being done. And after that line, we are assigning the respective values, that is
this line
star
is
p pointing level.
71 is not completed. We have explained the right hand side of 71. What about the left hand side?
So left hand side means, sir, didn't get that one.
রাইট হ্যান্ড সাইডের মানে হচ্ছে মেমোরি অ্যালোকেশন, একটা অ্যাড্রেস পেলাম, এরকম একটা ঘটনা ঘটলো।
ও আচ্ছা আচ্ছা, আপনি স্যার আচ্ছা লেফট হ্যান্ড সাইডটা মানে বলছেন। আচ্ছা স্টার পি,
এখন
অ্যাজ স্যার স্টার পি যখন ইয়েস স্যার স্টার পি as star p was previously null, now star p is assigned to this new node, that is star p will be equals to 3004.
এখানে হচ্ছে 304, ঠিক আছে,
Hmm.
304
Sir, 3004.
পিকচারে স্টার
Yes,
পি
sir.
এখানে
So star p is that one, sir, the real, yes sir, yes agree. In the sir that blue part you wrote the null. This one, yes sir, 1300 to connect all.
this, right?
Yes sir.
This
Yes,
value.
sir.
Okay, this value. So this should be
Yes
this
sir.
star pin is
3004.
so once it is 3004, now it is no
Connection will be made. Yes sir.
now it should point towards this. Okay, and then
Yes sir.
this nothing.
Now we are sir assigning the particular label, that is 13, and both the left and right be null.
Okay, so in this way insert BST is done. Similarly, you
Yes,
can
sir.
explain next value 8, which is going to be inserted somewhere here.
Yes
Eight,
sir.
right?
Left side.
So
Yes sir.
other students must be able to explain how the node 8 is being inserted here in terms of the program execution. Okay. Once you can explain, you will understand, and from the next time onwards, you will be able to code implement this kind of recursive based insertion. Or okay, so in the next class, I will be again showing you explaining you the program implementation of delete BST, which is the most important part tomorrow, and I will also discuss 233. So with this, let's stop here.
আচ্ছা স্যার একটা ডাউট ছিল
Sure.
স্যার। আচ্ছা স্যার, এটা কি স্যার রিকারসিভ ছাড়াও কি করা যেতে পারে? স্যার আমি জিজ্ঞেস করছি।
রিকারসিভ ছাড়াও করা যেতে পারে।
ওকে ওকে,
রিকারসিভে কোডটা একটু ছোট হয়ে যাবে।
ওকে
স্যার বলছি কল বাই রেফারেন্স ছাড়াও তো করা যেতে পারে।
হ্যাঁ, কল বাই রেফারেন্স ছাড়া করা যেতে পারে। তোমাকে আরেকটা ভেরিয়েবল তোমাকে গ্লোবালি ডিক্লেয়ার করতে হবে।
হ্যাঁ স্যার,
ফাংশনের ভেতর লোকালি ডিক্লেয়ার করে আর কি ওভার করেছি।
রুটটাকে যদি তোমাকে অ্যাক্সেস করতে হয়, ইনসার্ট যেমন রুটটাকে অ্যাক্সেস করছে, কিন্তু রুট নামের ভেরিয়েবলটাকে ইউজ করছে না, ওর অ্যাড্রেসের থ্রু দিয়ে তাকে ইউজ করছে। ঠিক আছে, রুটের অ্যাড্রেস কার কাছে আছে? পি এর কাছে। তো পি এর থ্রু দিয়ে রুটটাকে অ্যাক্সেস করছে প্রত্যেকটা ফাংশন, ইনসার্ট, ডিলিট, ইন অর্ডার সব। আর না হলে তোমাকে রুটটাকে গ্লোবালি ডিক্লেয়ার করতে হবে, মেইন ফাংশনের বাইরে, সবকটা ফাংশনের বাইরে গ্লোবালি। দুটো উপায় কালকে বলছিলাম, যে একটা পয়েন্টারকে যদি সবকটা ফাংশন ইউজ করতে চায়, তাহলে আইদার তাকে গ্লোবালি ডিক্লেয়ার করো, অথবা তার অ্যাড্রেসকে তুমি মেইন ফাংশন থ্রু দিয়ে পাস করো। মেইন ফাংশন থেকে যখন একটা ফাংশনকে কল করবে, তখন ওর অ্যাড্রেসটাকে পাস করে যাও, তখনই কল বাই রেফারেন্স। So either you declare it globally, or you can do call by reference based function call. দুটো উপায় রয়েছে। তো কল বাই রেফারেন্সটা নতুন কনসেপ্ট, তাই এর আগেও একটা ক্লাসে বোধহয় বুঝিয়েছিলাম লিঙ্ক লিস্টে, তাই ওটাকে আরেকবার বুঝলাম। পরীক্ষা আস্তে আস্তে তোমাদের প্রোগ্রামিং স্কিলটাকে বাড়াতে হবে, এনহ্যান্স করতে হবে। তো পরবর্তীকালে এগুলো তোমাদেরকে জিজ্ঞেস করবেই, বা এরকম টাইপের প্রবলেম ফেস করতে হবে। এনিওয়ে, ওকে, তাহলে এখানে স্টপ করলাম, আমি অ্যাটেন্ডেন্সটা নিয়ে নিই।